Welcome to this course Applied Thermodynamics. We are in module 3 internal combustion engine. In this we have the following list of topics. Out of this topic number 1 and 2 has been covered, and now we are in the topic number 3, that is engine operating characteristics. So, this particular topic we are going to discuss today. In the engine operating characteristics, the following segments we are going to cover. First, we will introduce within some important engine parameters, then we will discuss about mechanical and combustion performance of the engine, and then we have to discuss about the emission index, because that is the emission norms that every engine has to follow, and finally, we will end up in discussing the few characteristics curves, and that characteristics curves we try to see the particular trend that the performance, combustion and emission parameters should behave with respect to SI engine and CI engine. So, let me start with the first topic, that is engine operating parameters. So, when you discuss about the operating parameter, the first parameter that comes in is the compression ratio, and in fact, the compression ratio mostly decides the size of the engines. So, in the earlier developments, that means if you look at this particular plot, in the earlier development the engine starts with a compression ratio something in the 18th and 19th century with compression ratio in the range of 2 to 3. Then subsequently with time the compression ratio people try to increase. So, when you are trying to increase the compression ratio, then effectively we are looking into bigger size engines, and towards the end of 19th century or we have the typical compression ratio what we have, we come up in the range of 8 to 10. So, this is the plot that shows the typical trend that how engine development has occurred from last 2 centuries. Now, if you look at the compression ratio, then what other things that is more important is the fact that we need to characterize the engine performance. First with compression ratio, second apart from this we have to define certain user parameters in terms of range of power or torque and range of operating speeds. So, based on that we define 3 important parameters, that is maximum rated power, which is nothing but the highest power an engine is allowed to develop for a short durations. That means, the highest power is only obtained for a very short duration by the engine. The normal rated power, this is the highest power that engine is allowed to develop for continuous durations. So, engine is run for 1 hour, 2 hour, 5 hour, 8 hours. Likewise, how much power or highest power it can develops if we run for 8 hours or 10 hours a day. So, that is called as normal rated power. The third point is the rated speed. So, the rotational speed of the engine at which the rated power is developed. So, maximum rated power, normal rated power and rated speed. Now, to look into these particular parameters, we need to have some deciding factors. So, these deciding factors are the engine performance. Now, for example, if you want to run the engine at this maximum rated power or rated speed, then what should be my engine performance? Whether the engine has any issues while running at that rated speed or rated power, and that point of time what is the fuel consumption, because this fuel consumption leads to the cost of the fuel. Now, while doing so, whether there is any engine noise or pollutions. Now, by catering all of them, we also need to look into the reliability, durability, maintenance requirement for the engine. And apart from these 4 parameters, the other vital segment is the initial cost and its installation. So, that is mainly for static engine, and for transport sector we also require what is the cost of the engines. So, these are the deciding factors that a user is expected to know. Now, just to give a glimpses that what are the different types of engines we look into or we see in the market. So, the engine can have a very small displacement volume in the order of 0.075 cc or centimeter cube, and this engine also can operate at maybe at close to 35,000 rpm with a rated power output of 0.15 to 1.5 kilowatt. So, a small engine can also run at very high speed, but the power output may be less. But in that case also the engine speed could be average piston speed in the range of 5 to 20 meter per seconds. Other extreme could be we can run the engine at low RPM, but high displacement volume. So, these two things actually tells us that what should be our engine side and what are the its rated operation. By doing so, we will be able to characterize the engine performance. So, as I mentioned in the beginning, apart from this we have compression ratio, that is typically 8 to 11 for SI engines and 12 to 24 is for CI engines, that is mostly used for modern engines. Now, having said so, then we need to look into, let us say look into the matter that let us say that we have this compression, we have certain engine with some desired compression ratio, it has certain displacement volume and it is operated at certain rated RPM. Now, for this engine we need to use it for a particular application. So, now when we run the engines, we expect there are some input entries, sorry, or input parameters, there are some output parameters. The output parameters could be power, speed, work, torque, all these things, and input requirement could be the air fuel ratio, combustion efficiency, that means if the fuel is introduced in the engine, not necessarily that 100% of the fuel will be burnt. So, there is a combustion efficiency comes into picture. So, these are some input requirement and these are some output parameters. So, basically what the performance characteristics means or engine means, using these operating parameters we need to find out a correlations between the output parameters and input requirements. So, that is the main philosophy of discussion today. Apart from this, we also try to emphasize on the certain aspect of emission measurements. That means, if the combustion is not proper, then what else we are going to get in the engine exhaust, if whether those exhausts are desirable or undesirable for environmental point of view. So, all these things we can be possible only when we do some bench test and with some standard calculation procedures, and we are trying to map the results in the form of graphical nature and we call them as engine performance curves. So, this will be last part of the lecture, we are going to emphasize on this particular performance curves. So, let me start with the first one, that is mechanical and combustion performance of the engines. So, the first parameter what we are going to look at is the indicated power. So, as you know that we in thermodynamics we have been told that the pressure volume characteristics can be plotted graphically based on certain thermodynamic processes like constant pressure, constant volume, isentropic process. So, we will now touch upon similar plots, and in this philosophy of IC engine we call it as a indicator diagram. So, it is nothing but as the rate of work done by the gas on the piston and as evaluated from indicator diagram. This indicator diagram is nothing but a pressure volume diagram, and this pressure volume diagram is characterized in this fashion, and as shown in this figure, that is where we have a power loop and we have a pumping loop. The upper loop, that is the power loop, this power loop is nothing but the upper loop. It is consist of the compression stroke and power stroke with area representation as gross indicated work. So, the upper loop is known as, that means the area under the curve under the PV diagram in the upper loop or power loop is known as the gross indicated work, and the lower loop is known as pumping loop, and it is the negative work, and we call it as a indicated pump work. So, the net work per cycle would be the proportional to the difference in the area of power loop and pumping loop. This is one way representation of pressure volume diagram in thermodynamic sense, but with engine terminology we normally represent the volume as a mapping with the rotation in the crankshaft. So, that particular method we call this as a pressure crank angle diagram, and a typical curve of a pressure crank angle diagram is shown in these figures. So, in this particular two plots, what we have tried to show is that one PV plot that will give you the thermodynamic estimates, and that can be correlated with the rotational motion of the crankshaft. So, that is in terms of pressure crank angle diagram, and typically we have a concept of mean effective pressure. So, this mean effective pressure is nothing but a constant pressure line which can be represented in this PV diagram. What it says is that over a set of engine displacement or piston movement from TDC to BDC, what we see is that this is the area under the curve, and we call this as a gross indicated work, and that is the power loop, and the other side is that is negative work, that is in the pumping loop. So, we can calculate the net area. Now, imagine a situation that we want to evaluate an equivalent area which is same as this net area. So, for that case I will imagine a rectangle with a volume displacement volume from TDC to BDC and put a mean line, and I call it as a mean effective pressure line. So, the net area which can be drawn with this mean effective pressure line, and this happens to be a rectangle, then that particular pressure is known as mean effective pressure. So, actually the engine does not have a mean effective pressure, but we can represent them in our mathematical estimates. Okay. So, that there are standard methods in which this pressure volume diagram can be drawn when it is through an by a mechanism what we call as a piezoelectric setup, which is installed in the crankshaft, and from this crankshaft we will get a signal that can be recorded in an oscilloscope to plot the pressure variations, and this is known as pressure crank angle diagram. So, basically we can from the pressure crank angle diagram we can get back this indicator diagram, and this with our modern instrumentation and data acquisition systems and advanced electronics, we can incorporate to get the estimates in the work output in the from this indicated diagram, and from there also we can calculate the mean effective pressures. And from this mean effective pressure we can come back to the indicated power. How it will be followed in the next section. So, whatever I have explained, so we are going to represent in the mathematical form. So, the indicated mean effective pressure is defined as P I, that is equal to net area of the diagram, which means net area from the between the power loop and pumping loop. That means, from the power loop, if you subtract the area of the pumping loop, then you will get the net area, and length of the diagram is nothing but your motion, the piston motion from TDC to BDC, and that is known as L into constant. This is a typical constant which represents the parameter that depends on the recorder. So, this constant is a fixed constant with respect to instrument point of view. Now, from this indicated mean effective pressure, then we are going to calculate indicated power. How? Now, let us consider an engine with bore B, stroke S, and which has an engine RPM n, and this engine has a number of cylinders K. So, what we can write is that work done per cycle per cylinder is nothing but the pressure into volume. Pressure is indicated pressure is P I, and volume can be represented as area into S. S means area into stroke length, and this area is nothing but pi by 4 into B square, where B is the bore. So, once you know the work done per cycle per cylinder, then we can calculate the power output. That means, power output we can calculate work done per cycle into number of cycles per minute. Now, here you have to take the catch that what is this number of cycles per minute. So, number of cycles per minute is normally represented as n, and this n is equal to either n by 2, that is for 4 stroke, or n is equal to n, that is 2 stroke. Okay, because this n based on this, because this is the number of revolutions based on the number of revolutions of the crankshaft. So, accordingly, by putting the respective expressions, we can get back the indicated power I p as P I A S n into K, where K is the number of cylinders, and divided by 2. If it is a 4 stroke engine, there is no division of 2 if it is a 2 stroke engines. So, based on this indicated diagram, we are able to estimate the indicated power in terms of indicated mean effective pressure. Then next thing what we are going to discuss about brake power, friction power and mechanical efficiency. When we see the indicated power, it is at the engine input side. Now, from the engine output side, that means if the engine is run with, engine can be run with no load or with load. So, when we actually apply a load onto the engines, then basically we are braking the engine, and we interpret that as a brake power. And in the process of engine running, there are other losses that is taken into account as a friction power. So, these two terms go side by side, because as you increase the speed of the engine, this friction power comes down, and when engine speed is less, friction power is more. So, that point, so these two terms go side by side, and last term is the mechanical efficiency, which is nothing but the correlation between the brake power and the indicated power. Now, let us see that in what way we are going to get the estimates of brake power and friction power. So, just to explain this fact, I can say that the actual work available at the crankshaft we call this as a brake work, and it is less than the indicated work, which is because mainly it is mainly due to the friction and other parasitic load. Parasitic load means other than the engine loads. For example, in a car we have AC, we have lights, we have other auxiliaries that takes the power in the engine. Even we have fuel pump. So, all these instruments take the power from the shaft of the engine. So, these are treated as a parasitic load, which is nothing but the other than engine load. Other than engine load in our term means the other than the shaft power. So, this brake power is nothing but the measured output of an engine. Now, how do we measure this brake power? So, for that purpose dynamometers are used. So, what does the dynamometer do? They measure the torque, because engine is run at certain RPM, then they measure the torque. At maybe we can run the engine at different speeds and the loads, that is our input end, and these dynamometers try to measure the torque, and then from the torque and engine RPM we can calculate the power. So, what are the typical dynamometers? These dynamometers are called Prony brake, which is a mechanical type. It can be a hydraulic dynamometer, another kind of could be eddy current dynamometer, that is electrical, that is mostly used ones, and they observe energy output of the engines. So, all these I am not going to into details, because these are a different segment or topics as far as IC engine mainly is concerned, but in our philosophy we will just look into the fact that what does the how we measure the torque and power output from the dynamometer and try to correlate our engine operating parameters. So, in this so for brake power we require dynamometer, and then there is no estimate that there is no method in which we can directly get the friction power, but friction power is nothing but the difference between the indicated power and brake power. So, that is the power required to overcome the frictional resistance. So, once we know the indicated power, brake power, then we can calculate the mechanical efficiency. So, how we can write in this manner? So, first thing is that brake power, that is nothing but is equal to twice pi n is the RPM of the engine and T is the torque, and the torque is nothing but W into R. W is the engine load and R is the radius, that means the location at which we are going to measure the torque, or in this case it is the radius of the shaft. Then difference between these two will give you the friction power, that is Fp is equal to Ip minus Vp. Then we can calculate mechanical efficiency, which is nothing but the ratio of brake power to indicated power. So, here moving further, we need to give another insight to the fact, as I mentioned, that the brake power and friction power should be looked into simultaneously. So, this particular plot shows the variation of mechanical efficiency with brake power. That means, if you increase the brake power, the mechanical efficiency goes up. Normally, mechanical efficiency ratio of brake power to IP indicated power. Of course, indicated power is a fixed number. So, brake power has to change with the mechanical efficiency, and typically this is not a straight line, because the friction power is also playing another culprit. So, that is what it is not a linear trend. So, it is a kind of a trend that is observed here. Now, another concept we are going to discuss is that the friction power, how to calculate the friction power. So, when the engine is run without any brake load, then we call this as a motored engine. So, the word motored engine comes, and we also has another word we call as fired engine. So, in a motored engine we can say that the engine is running without any load, but in a fired engine intentionally dynamometer applies a load onto the engine. So, all these things we are going to calculate because we need to find out them the brake power, indicated power and mechanical efficiency. Another important point that I need to emphasize here is that when the load is decreased giving lower value of brake power, the mechanical efficiency decreases, and at 0 BP, that is 0 brake power with same engine speed, the engine develops just sufficient power to overcome the frictional resistance. That means, when there is no brake load, but still engine is running, so it develops a power and that power is consumed through this frictional resistance, and we call this as a friction power. To calculate all these things, there are some experimental methods what we call as motoring test, Morse test and Wilson curve. So, these are the typical standard methods in which we were going to calculate brake power, friction power and indicated power in the laboratory. So, first method what we are going to say is the motoring curve. So, the motoring curve, as I mentioned, the engine is run with a dynamometer, but that dynamometer does not provide the brake power, means that dynamometer is not used to apply load, but rather it is connected to a motor that consumes that power. That means, the entire power that is developed by the engine, it goes as a friction power. So, in other words, in a motored engine your brake power is 0, but friction power would be nothing but the indicated power. But in a fired engine where the dynamometer actually applies load to the engine, your brake power is not equal to 0. Of course, friction power is also not equal to 0. So, this is a real sense and this is a ideal sense that to estimate the friction power, and this is how the concept of motoring test is all about. So, in one case we have to run the engine in a motored conditions, and the other way we can run the engine in a fired conditions. So, based on that we can calculate the friction power. So, first thing, how do you do the motoring test? So, in the motoring during motoring test you connect the engine with a dynamometer, but that dynamometer should not will act as a motor, so that the brake power is 0 and friction power is nothing but the indicated power, and that means in this way we can calculate the friction power of the engine. So, once we know the friction power, and that can be done at different speeds. Different speeds means here this is plotted with average piston speed and we can correlate with as n. So, at every n, every RPM, one can find out what is the value of friction power. So, and that is nothing but the indicated power, because the brake power is 0. Another curve can be drawn with the fact that which is a plot between this friction power and RPM, or frictional mean effective pressure versus RPM. So, at that every point one can calculate, there are 2 points, that means at any n we will have 2 values, one for the fired engine, other for the motored engines, and difference between these two is nothing but the friction power, and this expression can be used for all RPMs. When you do all the RPMs, and then we can estimate the curve, that is brake power versus mechanical efficiency versus brake power, which comes in this fashion. So, it is not exactly a linear fashion, that is a parabolic nature. So, this is all about motoring curve that talks about how you are going to calculate the mechanical efficiency of the engine. Another test that we are going to do is a Morse test. So, this particular test, Morse test, is referred for either SI or CI, but with a condition that it should be a multi-cylinder engines. So, maybe this particular, that means this particular test is only applied for multi-cylinder engines. So, as you can see, there are number of cylinders 1, 2, 3 and we have k number of cylinders, and each cylinder is assigned has some indicated power I p 1, B p 1 and L 1. L 1 is nothing but the frictional losses. So, that means indicated losses. We can write I p 1 is equal to B p 1 plus L 1, I p 2 is equal to B p 2 plus L 2 and I p k is B p k plus L k. So, this is how for each cylinder we can note down. Okay. So, how we are going to estimate? So, first let us consider there are k number of cylinders in an engine. The indicated powers are defined as either I 1, I 2, I 3, I k, and this I 1 is nothing but this I p 1 and B 1, B 2, B k, L 1, L 2, L k. So, these are nothing but I 1 terms, these are nothing but B terms, that means indicated term and brake term. Now, to calculate the brake power of the engines, what we are going to do? We are subsequently cut each cylinders. So, when you cut each cylinders, that means for example, engine is first run with all the cylinders and you cut the cylinder 1. That means, you disconnect the cylinder 1 from this, but what happens is that since engine is running with all the cylinders, still although the it will not contribute the brake power, but it can contribute the friction to the entire running operations. So, the friction power remains there. So, this cutoff can be done either for SI or CI. For SI engines we can cut off the spark plug, for CI engine we can stop the fuel injection. So, thereby we can do this fuel cutoff. Now, once you do that, what we are going to get in our estimate is that when the engine is run with all the cylinders firing, we can calculate the brake power as I p 1 minus L 1 plus I p 2 minus L 2, that is the brake power of in each cylinder. So, this is cylinder 1, this is cylinder 2 and this is cylinder k. From this, when the first cylinder gets cut off, then we denote that as B p 1 with all other cylinders running. Then when the first cylinder is cut off, so its indicated power becomes 0. So, the expression, that same expression can be written in this manner with 0 term as I p 1. Similarly, when the second cylinder is cut off, the 0 term appears for I p 2. Likewise, when the case cylinder is cut off, 0 term appears for last case cylinder. So, likewise, we can find a relations B p minus B p 1 is equal to I p 1, B p minus B p 2 is I p 2 and so on. So, in this wise, if you sequentially add all these terms, we will end up getting a term that is I p is equal to I p 1 plus I p 2 plus I p k dot 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 I p k. So, that means total indicated power of all the cylinders. So, ultimately from the first expression we already know B p, we get the indicated power from this method and we get the mechanical efficiency. So, this is how the Morse test is conducted to calculate the mechanical efficiency of the engine. The last one is which is known as Wilson's curve, and this is mostly applied for a diesel engines, because in the diesel engine we have provisions of cutting off the fuel through fuel injector, and in fact it is only applied for that concept. So, what do you do is that a diesel engine is if you look at this particular plot, it is plot between fuel consumption and brake power. So, normally what happens, the brake power increases when we want to increase the brake power, we should increase the fuel consumptions. So, basically when the fuel gets injected, for every fuel consumption rate, we can estimate the brake power experimentally. So, so that means at this first point end defines the point at which the fuel is injected first, and slowly then we can get the another for different fuel injection value we can get different brake power. So, we can generate this data experimentally. So, these are basically experimental observation in which we keep on increasing the fuel consumption, we get the brake power. So, basically we get the curve A B from this experimentally observed data, and it will be treated as a straight line. Now, once you generate this curve, what you do is that this is with respect to a particular engine. Now, what you do is extrapolate this data from point A and try to see that where it cuts at the negative axis of this brake power. So, this cuts at the point C. So, if you take the origin as O, then OC can be considered as the friction power, and because it is negative to the power axis. So, in this fashion we get the friction power, and we also know the brake power. So, one can find out the relation between between the brake power. From these two expressions we can find out the mechanical efficiency, that is brake power by indicated power. Okay. So, now we are going to introduce another concept which is called as brake mean effective pressure. So, there is a correction here, it should be BMEP. So, the concept goes in a similar manner in which we defined the indicated pressure. So, I do not want to give more emphasis on this. So, we want to go into the same relation the way we did it for indicated power calculations. What we have seen in that case, in that diagram for calculations as the plot between pressure and volume diagram. But here we are going to plot the pressure and volume diagram at the output conditions. So, the output condition could be of two possibilities, one is wide open throttle, other is part throttle. So, wide open throttle condition means that your throttle valve is fully open. So, when the throttle valve is fully open, engine is allowed to run with full fuel capacity. That means, fuel can go into the engine to a maximum. Now, when there is a part throttle, that means engine is allowed to run with some partial amount of fuel. So, these are the typical concept that you use in the engines. Why use wide open or part throttle? Because the valve has certain finite element or finite amount of space which it is going to allow for the fuel to enter into the engines. So, if I say 100% open, I cannot ensure that 100% fuel is going, because the valve occupies certain space within that region. So, that is the word where you are using the wide open and part throttle conditions. Now, with the same concept of work calculations, we have introduced mean effective pressure into delta V, and here delta V is nothing but we calculated the piston displacement from TDC to BDC or BDC to TDC. So, that way we call it as a displacement volume. This mean effective pressure you are now going to use as a brake mean effective pressure. So, how you are going to do? First, we can calculate the brake power as mechanical efficiency of the engine into indicated power. So, in this way we can since we know the indicated power in our already calculations. So, we can write that expression is in terms of indicated pressure. Now, here we are going to introduce the term which is brake mean effective pressure PB. So, that is nothing but mechanical efficiency eta m into Pi. So, this is how we are going to calculate the brake power from this indicated power, but other way is that we can also get the brake power by using the dynamometer. That expression goes as twice by n into T. Now, if you equate these two terms, what we are going to find that this brake mean effective pressure is nothing but Pb is equal to some constant into T. That means, brake mean effective pressure is a direct indication of the torque developed by the engines. So, if you do that, so you can find that most of the term will get cancelled, other term like A and S becomes a constant. So, that is what the constant K appears here. So, in this way we can interpret the brake mean effective pressure for the engines, and this is written for 4 stroke, but for 2 stroke this n by 2 will be replaced as only n. However, in our situations we always use 4 strokes. So, we will go ahead with this expression. Apart from this, we are now going to discuss something about the thermal efficiency, combustion efficiency and specific fuel consumption. So, this is all about the mechanical aspects. Now, we are bringing into fuel into picture. So, when we are bringing fuel into picture, so that way we define 3 terms like brake thermal efficiency of the engine, which is nothing but the ratio of brake power to the fuel total fuel heating value. So, this is the output that we get from the engine, and this is the input we are providing in terms of the fuel. So, that is nothing but m dot f into QCV, QCV is your calorific value. In similar sense, we can also define the indicated thermal efficiency, that is equal to IP by m dot into QCV. So, the ratio of these two again turns out to be the fact that ratio of brake thermal efficiency to the indicated thermal efficiency becomes the mechanical efficiency. So, this is one aspect. We should not get confused that between thermal efficiency and mechanical efficiency. So, mechanical efficiency it is between brake power and indicated power, thermal efficiency is between brake power and the fuel heating value. So, these two terms should not be confused. So, apart from this fuel heating value, total fuel heating value can be correlated in terms of combustion efficiency, that is eta C. So, that is nothing but actual heat that is going into the engine from the fuel, that is termed as Q in, divided by total heating value of the fuel. So, this is how we say define this combustion efficiency. And there is another term which is called as specific fuel consumption. This is of more interest for the user, and it is mostly interpreted in the term of mass of the fuel consumed to divided by the brake power. Many of the books also represent as BSFC, that is also true, but in most of the spans we normally are not interested with indicated specific fuel consumption. So, mostly we interpret as a in terms of brake power. So, either you write SFC or BSSFC, it means has same meaning. So, just to give a number that for an engine to have, one should think that the fuel should have a combustion efficiency between 95 to 98%, and typically mechanical efficiency falls in the range of 0.8 to maybe 80 to 85%. Indicated thermal efficiency is typically 0.4 to 0.5 or 40 to 50%, and finally end result what we get, the indicated brake thermal efficiency of the engine for an IC engine is in the range of 0.3 to 0.35. So, in other words we say we are actually consuming the total 30% of the fuel energy. And in another terminology we are going to talk about something on volumetric efficiency, and this volumetric efficiency is defined as the ratio of total volume to the displacement volume, and this is volume of the air which is inducted to the swept volume of the engine. So, normally this volumetric efficiency word comes for gaseous fuel, and this term is not so significant in for liquid fuels, and this is very significant term for gaseous fuel. Most of the engines that use biogas or LPG or natural gas, that term volumetric efficiency plays a role, because if they has to be linked with air, because they have to mixed with air. So, accordingly how much air you require for a given fuel, that depends on the size of the engine, and this is affected by the speed of the engine, compression ratio of the engine, valve timing, mixture strength, cylinder temperatures, all these things are very vital part of this engine. As you can see from this plot, a typical trend will tell you that volumetric efficiency drops when engine speed increases. And then we have the emission index. This emission index means when the engine is run, there are some unwanted products that comes out of the engines, and they are treated as oxides of nitrogen, oxides of carbon monoxide, and hydrocarbons and other solid particulates. So, the common method of quantification is that by two means. One is in terms of specific emissions, that is how much grams of that particular gas comes out per kilowatt hour. This is one way of representation. Other way is that in terms of fuel consumption, that means how much mass flow rate means in the denominator instead of brake power, if you represent in terms of fuel consumption, that is m dot f. So, these expressions are listed here, and from the engine data one can calculate all these numbers and take appropriate way to calculate this emission index, and both are called as, either you can represent in the form of specific emissions or in the form of emission index. Now, here I am going to talk about some characteristics curves or trends, and first characteristics curve is the brake power or brake torque, which is a function of engine speed and displacement. So, as you see in this particular plot, it says that with engine speed, when the speed of the engine increases, the we also the first the torque or power also increases, but with a particular time it further drops. That is because when engine speed increases, your friction power also increases. So, the net loss is that it will drop the brake power, that is what it is known, brake torque also comes down, and there is a particular locations where the torque is maximum and it is termed as MBT, that is maximum brake torque, and it also appears the point at which the brake power is maximum. So, the trend of power curve or brake power curve is changing because your friction power is also changing with speed. Another term could be that brake specific fuel consumption as a fuel equivalence ratio. So, the fuel consumption is minimum when it is a slightly lean mixture. So, if you took a particular trend, so the fuel consumption is minimum. So, we can say the BSFC is the, that is brake specific fuel consumption is minimum at lean equivalence ratio. Another kind of plot that can be plotted is in the form of brake specific fuel consumptions as a function of engine speed and compression ratio. So, with increase in the engine speed, the brake specific fuel consumption drops, as I already mentioned, but what happens when you are increasing the compression ratio in this order, the brake specific fuel consumption drops, and the brake specific fuel consumption as a function of engine displacement. So, for a larger engines, so engine displacement is when it is increases, the specific fuel consumption also comes down, but it may not go at a higher speed, but with the displacement the engine speed, the base specific fuel consumption drops. Other specific characteristics curves that can be drawn for spark ignition, that is pressure volume diagram. We can also think about specific fuel consumption for fuel reach, exhaust gas content. Then in terms of emission norms with respect to air fuel ratio, we can think of carbon emissions with air fuel ratios. All these things are also very specific for characteristics curve, and they are in particular for SI engines. And for compression ignition engines, one can by running the engines by the method what I have explained, one can superimpose different curves to get the general trends for CI engines. So, when you define the characteristics curves you define two ways, one for CI engine, other is for SI engines. So, this is all about the lectures that I have the contents that I have delivered today. Now, we are going to solve some numerical problems based on this particular lecture. So, the first problem that we are going to solve is this fellows. We are going to discuss this problem in a step by step manner. So, we consider a 6 cylinder 3 liter capacity engines. It operates on a 4 stroke cycle and it operates with 3600 3600 rpm, and it is connected to a dynamometer that gives a torque reading 205 Newton into meter. We are also given with the mechanical efficiency of 85%, and we are supposed to calculate the brake power, indicated power, brake mean effective pressure, indicated mean effective pressure, friction power, friction mean effective pressure, and power loss due to friction. So, let me start the solution step by step. So, the first thing that we are going to see is that, so let me start the first problem. We need brake power, that is WB, that we can write as twice pi n into. So, this expression I have given in the lecture slide. So, once you know, here we have given here T tau. This T tau or torque we are given with 205 Newton into meter. So, n is 3600 rpm. So, from this we can easily calculate what is WB. So, WB turns out to be 77.25 kilowatt. Okay. The second problem is we have to calculate the indicated power. So, for indicated power we say, so here put W dot. So, it is a power turn. So, it is a put we have to in Wi dot. So, we know W dot B, we can divide it by mechanical efficiency, and we have already given this mechanical efficiency as 85%. So, it becomes 77.25 divided by 0.85. So, this turns out to be 90.9. So, we now are able to calculate the brake power, indicated power. Third term we are going to calculate as brake mean effective pressure, BMEP. So, for BMEP calculations, let us see that from this particular brake power expression, let us see what does this mean, W dot B by N, that is nothing but twice pi into tau, right. And this particular expression can be written as BMEP into VD, VD is your displacement volume, divided by N, N is the and this N is equal to 2, that is for 4 stroke, and 2 revolution per cycle. So, we know tau, we know VD, we do not know VD and we know N. So, calculate VD, what we are going to see that this is a 3 liter capacity. So, this VD can be represented as 3 liter, that is 0.003 meter cube. So, once you say this things, then we can calculate from this expression that BMEP, brake mean effective pressure, is equal to twice pi tau n into divided by BD. So, from this we can estimate BMEP as by putting this all numbers here, we can calculate it as 859 kilopascal. Okay. Then we are going to calculate the indicated mean effective pressure. So, this indicated mean effective pressure can be calculated from brake mean effective pressure, and this is expressed in this manner that we can write indicated mean effective pressure is equal to brake mean effective pressure divided by mechanical efficiency. So, it is 859 divided by mechanical efficiency is 0.85. So, this is about 1010 kilo Pascal. Then we are going to calculate the friction mean effective pressure FMEP, that is IMEP minus BMEP, and difference between these two is 1010 minus 859, this is 151 kPa. Then power lost to the friction. So, it is nothing but the friction power, and that is nothing but indicated power minus brake power. So, indicated power is 90.9 minus brake power is 77.25. So, this is 13.65 kPa. So, this is the clear cut expression of using the formula. The next problem that goes is that for the same engine specified in question 1, here the other data that is given as compression ratio, and this compression ratio is required because we need to calculate certain terms, and also other data is that here we are talking about the air fuel ratio, that is 15, and here air enters to the engine at certain condition 85 kilopascal and 60 degree centigrades. So, our main intention is to calculate the fuel flow rate into the engine, brake thermal efficiency, indicated thermal efficiency, volumetric efficiency, and brake specific fuel consumption. Now, let us start one by one. The first term that we are going to calculate, rate of fuel flow. So, to do that, let us see the mass flow or air fuel ratio, that is defined by MF is equal to MA divided by air fuel ratio. Now, here you do not know MA. So, to calculate MA, we are going to recall that it is a ideal gas equation, that is P V by R T, and here V is nothing but your displacement volume plus clearance volume, that is total volume, and R T. Now, we do not know the displacement volume and clearance volume. To calculate all these things, what we know is the compression ratio. So, you start your calculation with compression ratio is as 9.5. So, this will give you V d plus V c by V c as 9.5, and it is a 6 cylinder. So, 6 cylinder engine. So, that means V d becomes for this compression ratio calculation will be total 3 liter capacity. So, 3 by 6, that means 0.5 liter. So, we know V d and we know compression ratio. So, from this we can calculate V c as 0.0006 meter cube. So, V c known, so V d known. So, from this we can get this particular term. So, we can take R as 2887, just assuming that mostly it is air, joule per kg Kelvin. Pressure value is given 60 degree centigrade in which air is temperature is 60 degree centigrade in which air is entered, that is 60 plus 273 Kelvin. Pressure is 85 kilopascal. So, putting all these numbers, we can get the information about mass flow rate, or only mass of the air which is going into the engine as 0.005 kg, because we know P, we know V, V is nothing but these two this plus this. So, these two we know this, R known, T known, then we can get MA. So, once you know MA, then you come back here. So, we put 0.005 divided by airfoil ratio is 15. So, this turns out to be 0003 4033 kg per cylinder per cycle. So, this mass flow can be correlated to mass flow rate m dot f, that is nothing but this number into 6 cylinder into number of cycles is n by 2 3600 by 60. Then this 2 is for 4 stroke engine. So, this will give you m dot as f as 0.006 kg per second. So, we are able to estimate the first term, that is fuel flow rate. Then second term eta brake thermal efficiency, that is nothing but W dot P by m dot f into QCV into combustion efficiency. So, combustion efficiency is 97%, QCV is 44 megajoule or 44,000 kilojoule per kg. Then m dot f is known. So, from and bit W dot B we already calculated as 77.25 kilowatt, that is from the question 1. So, by putting all this expression we can get efficiency, brake thermal efficiency as 30% or 0.3. Then once you have brake thermal efficiency, then we can calculate indicated thermal efficiency eta T I as eta T BTE divided by mechanical efficiency. So, this is 0.3 by 8.85. So, this turns out to be 35%. Then we need to know volumetric efficiency. So, volumetric efficiency we can define MA by rho A into BD. So, the MA, which is mass of the air, which we already calculated as 0.005 kg, rho A, that is density of air, that is 1.2 kg per meter cube, displacement volume BD, which is 0.005 meter cube. By putting all these things we can get volumetric efficiency as 85% or 0.85. The last part is brake specific fuel consumption, BSFC, that is nothing but we can get the ratio as m dot f divided by W dot B. So, m dot B is 0.006 already calculated, but W dot B is 77.3. So, that is kilowatt. So, it is kg per second. So, if you simplify it, we are going to get 7.76 into 10 to the power minus 5 kg per kilowatt second. So, this is all the numbers in which we are going to calculate. And the last problem is on Moore's test. So, this particular derivation I have already indicated in the lecture class. So, here I just want to emphasize that the engine is a 4-cylinder engine 1, 2, 3, 4. For each engine it has each engine the brake load is measured as 110.8, 106.5, 104.2 and 110.2 Newton. So, what does this mean? That total brake load is already given as 160 Newton. So, total BP we have been given 160 Newton and BP 1 is 110.8 Newton, BP 2 106.5 Newton, BP 3 104.2 Newton and BP 4 110.2 Newton. So, from this we can calculate IP 1 is equal to BP minus BP 1. Likewise, we get 49.2 Newton. Similarly, IP 2 BP minus BP 2, that turns out to be 53.5 Newton. IP 3 BP minus BP 3 55.8 Newton, IP 4 BP minus BP 4 49.8 Newton. So, total indicated power we can sum it off. IP total indicated power will be 208.3 Newton. So, we already know BP, we know indicated power. Since our engine is running at same RPM at all the cases, so we can directly say that mechanical efficiency is nothing but BP by IP, that is 160 by 208.3. So, this is 76.8%. So, remember one thing, we have given with the load, okay, but our analysis was done in IP 1, IP 2, IP 3 because intentionally 2800 RPM is common for all the loads. So, N will get cancelled. So, in this way we can calculate the indicated load IP as 208.3 Newton or the mechanical efficiency is 76.8%. So, with this I will conclude this lecture. Thank you for your attention.